Hi everyone. I'm going to talk about efficient agreement over Byzantine gossip. This is joint work with Ran Cohen and Julian Loss. So let's first talk about what we're trying to achieve, which is large-scale consensus. In a classic consensus protocol, n parties each have an input and they want to agree on a joint output. Now, this has been studied since the 80s, and the first protocols required all-to-all communication, that is, n-squared messages. But unfortunately, in an internet setting where we could have thousands of parties participating, n-squared communication is not feasible. So what we want to do is to scale consensus protocols to thousands or tens of thousands of parties. And we actually have some nice solutions to this, both in theory and in practice. In theory, the leading solution is to elect subcommittees. Instead of having everyone speak, we have only a small committee of size M that's dependent on the security parameter rather than the total number of parties who perform the protocol between themselves. Of course, all the parties still have to listen to the committee, so the total communication can still be large. In practice, when we have thousands or tens of thousands of parties communicating, they can't communicate directly on point-to-point links. Instead, we use gossip networks. In a gossip network, parties forward the messages they receive to their neighbors and thus flood the entire communication graph with their messages. The communication in a gossip network depends on the number of edges in the communication graph. If we use a sparse graph, this can be quasi-linear in the number of parties. So the total communication now can depend on the size of the committee times the number of edges. Okay, so we want to run a protocol that elects committees. How do we choose the size of the committee? Well, the standard way to do this, assuming that the committee is elected uniformly at random from the entire population, is to first fix the probability that we're willing to tolerate error. What's the probability of a bad committee? And then take some assumption, some upper bound on the fraction of corrupt parties in the population. This allows us to compute a lower bound for the size of the committee we need. So for example, if we want to run an honest majority consensus algorithm, a good committee is one that has more than half of the parties honest. And a standard error probability that's used widely in practice is something like 2 to the minus 40. So given these two values, we can now compute the size of the committee we need given an assumption on the corruption rate. For example, if the adversary can only corrupt up to a third of the parties, then we'll need committees of size 600. But if the adversary can corrupt more, for example, if it could corrupt 2/5 of the parties, then we might need committees of size 1700 or more. So this is still too large for protocols that require m-squared communication in the internet setting. Therefore, we do need to use gossip to reduce the communication. So how do we model the gossip? Well, one way to do that is not to model it at all, but to include the communication graph explicitly as part of our protocol. So this works, but it's not a general solution. And the main drawback is that anytime we change our underlying communication protocol, we'll need to reanalyze also our consensus protocol. So it's much nicer to be able to define some abstract primitive that we can use as a black box. And we do have several different gossip definitions that we can use. On one side of the scale, we have the multicast definition. This is a cheap primitive, but quite weak. And on the other hand, we have, on the other side of the scale, we have the guaranteed delivery gossip, which is much stronger, but also more expensive. So to compare, the multicast protocol, if we're running it as a standard flooding implementation, is send a message to all your neighbors and forward at most one message per sender to every neighbor. For guaranteed delivery, we also start by sending the message to all the neighbors, but now we forward every message from the sender, no matter how many messages a given sender sends. So in terms of utility, as we said, the guaranteed delivery is actually quite a strong result. And if we could do this efficiently, then we could actually reduce our communication requirements from Byzantine agreement quite a lot. Multicast is not that helpful. And in fact, many Byzantine agreement protocols that use multicast include an explicit echo step because they need something stronger. However, multicast is very cheap. It can be done in communication that depends only on the number of edges and the number of committee members, the number of senders, whereas the guaranteed delivery requires a much more expensive communication cost. So what are our contributions in this work? Well, first, we have a theoretical contribution. We define an abstraction of gossip that we call gossip with a board that lies somewhere in the middle between guaranteed delivery and multicast. It's almost as useful as guaranteed delivery, and we show that it can actually be used to reduce communication costs quite a bit. But the worst case communication bound is almost as good as multicast, and it's just about as easy to implement. Again, here we'll need some extra assumption about the connectivity of the graph, but this is true for every protocol that uses gossip. Secondly, we construct a new concretely efficient Byzantine agreement scheme based on gossip with abort. Now, I want to note that this isn't the first time that gossip has been used to improve communication in consensus protocols. Previous work by Momos and Ren and by Tsimos, Loss, and Papamantu also did this, but they used explicit gossip constructions, and they didn't optimize the concrete parameters, only the asymptotic ones. In contrast, our protocol is concretely very efficient. It's 25 times better than the state-of-the-art Byzantine agreement if we take real-world committee sizes. Again, there's a caveat. We're comparing to protocols that do not require trusted setup. For example, the ADDNR protocol, published in this conference several years ago, did get similar communication complexity, but they required threshold signatures to reach this level of communication, and threshold signatures require a trusted setup. Secondly, our protocol works directly in a graded PKI model, which means the parties don't need to fully agree on who's participating. This means it natively supports permissionless protocols. And that's not a coincidence. The original motivation for this work was that we used Byzantine agreement as part of the Space Mesh blockchain protocol, and the state of the art simply was not good enough in terms of the practical parameters. This protocol has actually been deployed in practice on Space Mesh mainnet, and it indeed improves the communication by an order of magnitude. Finally, our protocol achieves agreement on sets. That is, the inputs and the output of the protocol are sets rather than bits or strings. And the nice property this has is that we can use this kind of agreement to bootstrap from a graded PKI to a full PKI by having the set of keys we think should be included in the PKI as our input sets. So what is a graded PKI and why do we care? Well, in a graded PKI, every party has a signature key pair, but there's no central bulletin board where all the keys are written. So parties might not know the other party's keys. However, when they receive a verification key, they can compute a grade for this key between 1 and D. Here, D is a parameter of the setting. And the parties may not fully agree, but they do partially agree. That is, for any given key, honest parties can disagree on the grade for this key by at most 1. So where does this come up? So it comes up often in permissionless settings. For example, suppose we're using proof of work in order to decide who participates as the committee member in this Byzantine agreement protocol. So how does this work? Parties generate their own keys. They don't tell anybody else. Here we have Alice, Bob, and Eve generating their own keys. And in order to participate, in order to be allowed to talk, they must solve a proof of work. And the proof of work needs to be, it has a difficulty parameter. The difficulty of the proof of work needs to depend on the total number of parties because we want the size of the committee to have a constant expected size. In this case, parties might not completely agree on how many parties are participating. For example, Alice and Eve both know that there are 3 parties participating in the protocol, but Bob, who doesn't see Eve, thinks there are only 2. So Bob's proof of work threshold is lower than Alice and Eve's threshold. This lets us use the proof of work difficulty threshold as a grade. And now, depending on how much the height of the threshold you passed, we give your key a different grade. Of course, honest parties are going to talk only if their own proof of work is better than the grade they think, the threshold they think they need plus 1. This guarantees that if, say, Bob thinks he's eligible, then Alice will agree that he's eligible with the highest grade. So that was graded PKI. How do we define gossip with abort, our new gossip primitive? Well, in gossip with abort, we have a sender with some public key, and the sender wants to gossip a value v. We have two guarantees here. The validity guarantee means that if the sender is honest and calls the gossip primitive at round r, then every honest party will output the value tuple, that is the sender's key and the value, by round r plus 1 with the maximum possible grade. The consistency guarantee is that if a value tuple was output by an honest party at round r with some grade g greater than 1, then every honest party will output the same value tuple at most by the next round and with a grade at least g minus 1. Okay, if you notice closely, this is actually the guaranteed delivery definition of consistency. So this is too strong. What we actually do is we weaken this definition a little bit and say, if the sender is not honest, then it's possible that some honest parties will output a different value tuple. However, it can either be the exact same one or one that has a special bot symbol indicating that they know the sender is malicious. In that case, they might not receive the original value. So how do we implement gossip with abort over a sparse communication graph? Essentially, we use the regular flooding protocol with a very small modification. The modification is that if we receive two different signed messages from the same sender, that is, we know the sender is cheating, then we replace the messages with an equivocation proof. We just need to prove to other nodes that this sender is cheating, and we no longer care about what value it's sending. And the grade here is going to be based just on the PKI grade. So for example, if we're using standard flooding, the first 3 rounds are identical to the regular flooding protocol, because up to this point, every node, every honest node, has only received a single message from the sender. Here the sender is node 14, and it's malicious. It sent 3 different messages, 1 to each neighbor. Now, after the 3rd round, there are 5 nodes in this example that detected malfeasance already. They received 2 different messages from the same sender. So what they're going to do is they're going to send equivocation proofs to all their neighbors rather than the value. And the reason this lets us improve complexity is the equivocation proofs might be different. So honest parties no longer have to agree on the equivocation proof. They might get an equivocation proof that's green and blue, or they might get an equivocation proof that's purple and green. And because we don't care that they agree on the equivocation proofs, we can show that every edge in the communication graph will have at most 2 messages per committee member. So this lets us bound the worst case communication complexity with this kind of gossip. Okay, so how do we use gossip with abort? So I'm going to show how it's used to construct a simple primitive. We use this in our more complex Byzantine agreement protocol. The simple primitive we call threshold gossip, which is an abstraction of a very common pattern in consensus protocols, that of count f+1 signatures on some value. Here f is a bound on the number of faulty parties. So this is a common pattern because it guarantees that at least one honest party must have signed this value. So parties call threshold gossip with some value x, and our guarantees are 3. 1, if f+1 honest parties actually did call threshold gossip with the same input value, then every honest party will output this value with the maximum possible grade. Soundness is that if any honest party outputs a value, then at least one honest party must have called threshold gossip. This is the same thing we require from the count f+1 signatures. And finally, consistency. If any honest party outputs a value with grade greater than 1, then every honest party will also output the value with grade at least g minus 1. So note that here we're no longer allowing abort. We can do this because of the f+1 requirement. So I'm not going to talk about the graded consistency because that's a little bit more delicate, even though not that complex. It just doesn't fit in our time. So how do we implement this threshold gossip protocol? Well, it's quite simple. In order to gossip something, we call the graded gossip with the same value. And then we record all messages we receive from graded gossip. Now, each message consists of a sender key, a value, and a grade. And we're going to partition the sender keys into sets depending on value. So the set for value v is a set of all keys from which we received exactly one message from gossip with that value. However, we might also have some malicious messages. So if we received a bot from the gossip, or if we received a value and a bot, then this key is part of the malicious key set. And our criterion for output is if for any value, the total number of value keys, the valid keys, plus the total number of malicious keys is more than f+1, we're going to output this value. And the intuition is we can count a malicious key as signing any value, because a malicious party could sign any value. And an adversary cannot invalidate a value by sending a bot, because this will only move the key from a valid set to the malicious set and won't change the total count. So how do we construct Byzantine agreement from this? Well, the high-level intuition is basically use the structure of the ADDNR protocol, communicating only over gradecast and threshold gossip, and replace the transferable certificates from ADDNR with the gossip guarantees. We're going to grade messages by the time they arrive, and by the PKI grade together. Since we're already grading messages by the time they arrive, we get this graded PKI for free in the protocol. And of course, our protocol uses existing techniques, but as anyone who's ever constructed and analyzed a Byzantine agreement protocol knows, the devil here is in the details. Making sure everything works together to get a secure protocol is what's actually hard here. So that's it for today. Thank you for listening, and I think there's a little bit of time for questions.